Hello everyone. Today we're going to be talking about transient tasks and how they relate to async and the problem they solve. So let's write some code. One of the issues that is very important to me is resource lifetime. And that manifests in lots of different ways, but the most simple example I can give looks something like this. Now, if you run this code, it will never exit. And the reason why that is happening is because this line here made a persistent HTTP connection to Google. And that's actually spawned a task, and that task has not exited. There are two ways we can force that task to exit, but first let's have a quick look at what that actually looks like. So we're going to go, we're going to get the current task. We're going to print the hierarchy of all the tasks. So we're going to come back here and run that and have a look at what's going on. So here's the reactor at the top of the tree, and here is the task which has connected to Google, and here is the task which is reading HTTP2 frames from that connection. And even though this task finishes, there's still that task in the background reading HTTP2 frames. So the first way we can ensure to close the internet. And if we do this, then that will correctly shut down the background task. And this is kind of the typical way of doing this, and it does make sense. Like, it's logical. You open a resource here and you close it here. And there are different ways you can do that. Like, you could do a syntactic kind of approach where you go internet.with, do whatever, and then somehow that internally calls close. But there is a problem which I became aware of when I was actually implementing a more complicated situation. So there is this tool that I was improving called GitHub Changelog Generator. Did I stick it in here? Yeah, I did. Great. Oh, for some reason, Adam is really slow today. Maybe it's just slow every day. Right. So, I recently retrofitted this code base with Async HTTP Faraday, which is an adapter to use Faraday to adapt Faraday to use async HTTP. And we did make a pretty big improvement, like between 20 to 40% improvement on throughput, just because we can improve the concurrency quite a bit. This code base is a little bit tricky to understand, but essentially there are lots of entry points into code which can use async HTTP Faraday. Now, the way that I implemented this is in this function, say fetch events async, what we do is we get the client, and this is the client which, this is Faraday, and it's a Faraday stack which eventually goes via async HTTP. And then we issue a bunch of requests here, and we do this with as much concurrency as possible. And then finally, we wait till all those requests to finish, and we call client.agent.close. And so what this does is it closes any persistent connections so that this block won't hang, because there aren't any, or if there were any HTTP2 tasks created in this block, they will be cleaned up on this line. But the problem with that approach is we don't always guarantee that this function is called outside of an async block. There could be another async block which is wrapping this function call, and that async block could actually be using the client to make requests. And so by calling client.agent.close, we're actually synchronizing all the clients, all the connections, all the open connections, all those requests have to have finished, which isn't necessarily guaranteed if there's an outer block which might be doing its own set of requests. So this is kind of a fundamental issue with using a shared resource and having to manage that state. And so this is the problem that I'm trying to solve. How can we get rid of this line? How can we implicitly call this line when we're going out of scope, when async is actually going out of scope? So I spent a long time thinking about this issue. Like, this is an issue that's been in my mind for many, even years potentially. Looking at, my opinion was very strong that this is the best approach that I can think of. You open the resource, you use the resource, and then you close the resource. And I think, my opinion was that was a logical thing to do. But it turns out when you're retrofitting existing code, you don't always have the liberty of knowing the exact state or scope in which this particular block of async will be running in. And so that brings the additional element of not knowing when is the right time to call this. And so I thought about it a lot, and I think it came to me, the right time to call this method, if it's not done explicitly, then there should be a point where you can call it implicitly. And that is actually when all the tasks have completed, all the natural tasks that the user has created and is expecting to execute. Once all those tasks have executed, then naturally you can close the resource because there's no tasks that are going to use it. And so that's why I wanted to introduce this new concept of transient tasks. And what a transient task is essentially a way of describing this relationship. So what this task does is we've marked it as transient, and I'll explain what that specifically means in a moment. And then we just have some kind of loop, and it can actually be doing real work. Like, for example, if you had a pool of resources like you do with HTTP, you might use this as a task every 60 seconds to go through and close any connections which haven't been used for, say, longer than 60 seconds. So it could be a way of cleaning up resources as well as closing the whole thing outright. But anyway, right now we're just sleeping forever. And it seems odd, how does this actually fail to the point where this line gets executed? But what happens is when this top level task is executed and comes out the end here, then there is no more user code to execute. At which point, async says, well, the user code is finished, therefore I'm going to stop any tasks that are still running, which includes the transient tasks. And so what async does is at the end here, it will actually stop this task automatically, which will cause the internet connection to be closed. So it's a kind of interesting design, and it's a way of doing resource management which is not scoped to the task, but scoped to the Reactor lifetime. And it still fits in pretty well with the overall design. I don't like introducing additional complexities if I don't need to. And this is one I thought about a lot. And this is still just really in a trial or testing phase. I hope to try it out and live stream the whole lot. But we'll see how we go. Like, there's every chance that there's some critical reason why I can't merge this or put it into master. But you know, so far it makes sense to me. So let's have a look at how it's implemented and what we're going to do to make it work. So unfortunately, I already implemented like most of the guts of it. So I'll go through it because I think this is kind of an interesting detail of async, which is not necessarily well known. So you saw earlier that you could print the hierarchy of all the tasks. And so all the tasks that you do in async are organized into a hierarchy. And the value of this is that you can stop branches of that hierarchy. So if you start a server, then any tasks that that server creates, you can stop them without knowing what they are. And that's quite a nice thing from the point of view of resource management, because you can just go, I'm done with the server. I don't care what it was doing, making like HTTP requests, doing DNS lookups, doing database queries. I want to stop all of it. And so you stop that server, and it also stops all of its children concurrency. Right. So this tree is implemented in a way to try and make it as efficient as possible. Actually, one day I would like to implement this in C, because there's a ton of like performance opportunities that you could gain by implementing this in C that you can't really extract when you write it in Ruby with hash tables for children and stuff like that. But it's okay, it's not too bad. So what I've done is I've added an argument, a keyword argument called transient, and I've made a slight optimization. We keep track of, for this node, and also the reactor itself is a node, we keep track of the number of transient children. And there's a couple of accesses which help us just, help with tests and so on. So then what happens is there are a couple of methods that we need to be aware of. So the first one is this one, add child. So if you have a node, the reactor, and you make a task using async, async will add that task to the reactor using this method, add child. And what this does is it lazy initializes the children of this node, and it adds that child to that list. And then finally, if the child was transient, then it increases the transients count. And this is sort of an optimization to minimize having to scan through this list to figure out if they're all transient or not. If the size of this list is equal to this count, then we know that all of the children are transient. And in particular, that condition plays into this method here, which is very critical. We'll see where this is used. Whether a particular node is finished or not. And so what this essentially is tracking is whether a node has any more work to do. And so we know this node itself is just an abstraction. And so this node does not represent any work. So it's finished if it doesn't have any children, or the children is empty, or the children are all transient. Those are the three things that will cause this node to be marked as finished. And then finally, when a task finishes, like an actual async task, it will call this method called consume. And what consume does is it tries to efficiently remove itself from the task tree. And so what that does is if there's a parent and it is itself finished, then it will reap itself from the parent. Reap actually just deletes itself from the list of children and updates the transient count. And actually this is a new piece of code which I added, which moves all the grandchildren which are not finished to the parent. And so this is kind of a little bit of a shuffle to move the transient tasks up the tree. Then finally we call parent.consume, so we apply the same logic to the parent, because the parent could be finished waiting on a child to finish, and this will collapse the whole tree. This is the recursive step which causes the whole tree to collapse if all the tasks are finished. And finally you have the last task at the very bottom at the leaf of the tree is finished, and then all of them will collapse all the way up. Right, so what that looks like in terms of the specs, let's have a look at that. So we have in the spec, there is a subject, which is just a node. And then we have a middle node, which is has the subject as the parent. And we have a child, which is transient, and the parent is the middle node. So we can print that out and have a quick look at what that looks like. Hold on. Yeah, it's not working. Node spec 120. What have I commented out that I didn't mean to? Okay, great. Subject print hierarchy, and it's coming out of that. Okay, so this is our hierarchy. There is the subject, the middle node, and the child, which is transient. And so we're just going to make some basic assertions about those nodes. So we expect the child to be transient, we expect the middle to be finished, because all these nodes are finished by default because they don't actually, as I said, they're abstract, they don't actually have any work to do. And finally, we're going to make finished pretend to be something that can do work. So allow child to receive finished and return false. Alright, so that's all passing. And so then what we're going to do is we're going to consume the middle node. And so the critical point is, this is like a user's task. And that user's task has spawned a transient node, which we expect to use to tidy up at the end of the reactor. So what we're going to do is, let's see. Well, we know what the hierarchy looks like before. Let's just go subject print hierarchy there. And so what we now see is that middle node is gone and the transient node is moved up to the parent. And so this is kind of the inductive step, I guess. This spec is trying to show that the tree behaves correctly. I'm not completely convinced that I've actually written the code correctly, but it looks okay for the moment. And then there's some additional assertions. And finally, what we expect to do is, once we have this arrangement, the parent, even though the parent has a child node, which is not finished, the parent itself is finished. We expect the subject to be finished. And this is the critical point, because we expect at this point all the user's code is finished, but there's still a transient task that's still running. And then at that point, what we want to do is we want to stop. We want this stop method to propagate down the tree and stop everything, including the transient tasks. So this is really the critical point. It's saying, the user code has finished, even though there's still this transient task sitting there, and then what we do is we stop that. So let's go and have a look at how that works in the reactor. So the reactor has this method called run once. It's kind of typical reactor style run loop method. What this does is it has a variety of things that it can do to execute tasks. So there's this ready list, which it can go through and resume all of those things that are ready to go and execute them. And then finally we get to this critical point here, which I've made some slight changes already, but I'll explain how it works. So this is self is the reactor. And if the reactor is finished, then we call stop. And this will stop any transient tasks as well. And so what this does is, this says, are we finished, excluding all transient tasks? And then this says stop all tasks, including transient tasks. And so this is really the key logic that says, okay, well, all the user work is done, therefore let's tidy up. And so let's go and have a look at how that works in about the simplest example I can make without being too, the simplest example I can think of that shows what's going on. Right, so we have a top level async block, and we have a task which sleeps for 1 second and then exits. And then we have this other task which is transient, and all it does is it loops and prints out the hierarchy and sleeps. And then finally it just says I'm exiting. And so if we don't mark this as transient, what happens is it just keeps on going forever, right? Because, let me just run it in the terminal so I can get the font size a little bit bigger. So this will loop forever because the reactor has one child running. This task, that's the outer task, and this task, which is this task. And so the reactor will just keep on going because this task is never finished. And what we want to mark this task, make it transient, so that when all the other tasks are finished, this task gets stopped. And so if we mark that task as transient now, what's going to happen is the tree will compact, and the reactor will see that the reactor itself has finished because it only has transient tasks left running, and that will cause the code to exit. So transient task exited with async stop, which is exactly what we wanted. So the interesting thing about this is, how do we fit this into a more complicated example? And so coming back to GitHub Changelog Generator, like I said, we want to remove this line here. We want to defer that to a transient task. In fact, we don't want to have any code in here which even cares about that stuff, because in my opinion, that's just wrong. We shouldn't have it in there. So there is a gem which I made called Async Pull. And what Async Pull does is it implements a resource pull, singleplex and multiplex resource pulls. And so what we want is we want a way for this pull to close itself when it goes out of scope. And I'm not sure if I should just build it into the pull directly, or if it should be sort of an additional bit that you can opt into. I kind of think it should just be by default, because it makes the most sense that if you go out of scope with async, that the pull just cleans itself up. So first, let's write a spec. Let's see if we can write a spec. One of the things that is really important to me is that the semantic model is correct. And I know that's a pretty big, can be a big leap of faith at times, because you have to make assumptions about what it is you want to do. And my concern about introducing transient tasks is the model is that it introduces makes the code unnecessarily complicated in some way. And the problem is, it's not that transient tasks themselves are complicated, but that they introduce behavioral interactions with other parts of the system that could be unpredictable. And that is something which, as you introduce more features, as you increase the surface area of your code, you end up with features that interact in ways which become unpredictable or cause unpredictable sequence of operations. And that's something you want to be really aware of when building these kinds of abstractions, in my opinion, because the goal here is to build something which people can use in their own code and feel that it's predictable. But definitely expecting users to call close, the question then becomes, when do you call close? And so that's what I want to try and solve. I want to try and make it so that users don't have to understand when they should call close. And I also don't like that responsibility being up to the garbage collector, because the garbage collector is so unpredictable. And so my goal here is to have, it's sort of almost like garbage collection. It says, when all the user code is finished, do this particular thing. And so that's the abstraction I'm trying to create. It's almost like a garbage collector, because you've gone out of scope by that point. It closes all resources when going out of scope. Right, so I don't know if this pull is set up to actually do anything. It looks like it just generates objects. Okay, so let's grab that. The other thing that concerns me about this is when you have a transient task which you stop, that transient task may start other tasks to finish closing itself. And so I'm thinking of putting guards in so that when you stop a task, it cannot create more children tasks, because that could just lead to it can lead to a disaster, which would be problematic. Now, is this all running inside a reactor? Oh, it is. Okay. We might need to make a different context, because I think that runs all the specs inside a reactor, which is a problem. That is okay. This is kind of a unique thing to be testing. Okay, right, so we have a pull controller, close, it closes all resources and going to scope. Okay, so what we want to do is we want to acquire and then release. We want to put that in an async block, and then what we want to do is we want to expect subject so what this line is asserting is there is some and then what we want is we want to come out of scope, expect subject right, so as we come out of this block, we want to trigger that to close. So let's try running that. Now the first thing we're going to do is we're going to point that code at the updated async with my current work. And then we are going to update. Wow, that's exciting. No. Bundle exec spec dash e, and what was the test called? Going out of scope. Wrong number of arguments. Awesome. Okay, I think I need to include that line. The Async Pull resource is a base class which includes the methods that are required for resource management. Concurrency is one or more. So on HTTP 1, for example, this returns 1. On HTTP 2, it returns the maximum stream count defined by the HTTP 2 settings. Count is just a useful statistic, how many times the resource has been used. And I feel like we should add a timestamp as well, like last used time, so we can do better pruning. Viable is whether this resource is still good. Closed is whether the resource has been closed. Close itself is just obvious. And reusable is whether the resource can be reused. So these all get triggered at different points. Some of them look very similar, but semantically they get used at different points in the lifetime of the resource. And so things like viable and reusable have different timing characteristics. Like I think reusable is checked at when you put a resource back into the pool, whereas viable is used when you try and pull a resource out of the pool. And so when you're dealing with HTTP, there are different ways in which you need to figure that out. Okay, right, so let's come back here. So that subject is set up correctly, so it should just basically fail. Yeah, so it was not empty. I expected it to be empty, but it wasn't. So basically what we want is something like this. True. Test.sleep, and I don't know, I probably should just make like a sleep forever thing because that seems logical to me. But let's just do that. I guess I can make like 60. And actually the pull is an operation to prune, so it could be a nice thing to do. Actually, let's just do it because it should be fun. Subject prune, test.sleep 60. I don't think that's going to trigger, but that is probably the logic we want. Right, so there we go. That's awesome. I'm so happy to see that. So what happened here was we created the object pool, we acquired an object from it, we checked that the object was valid, we put the object back in the pool. It can be anything like a connection to a database server, a file, it could just be anything at all. Then we checked that the resources is the available resources in the pool, and it wasn't empty because we just put one back in. And then what we did is we spin up a task which does this, and it prunes the pool every 60 seconds, and then finally it closes the pool. And that's marked as transient, so that when we come out of the reactor here, it basically guarantees that the pool is closed. And that also means that the pool won't stay around. So this doesn't solve all the problems yet, because the background tasks for HTTP2 are not marked as transient, and those tasks actually should probably be marked as transient. So let's go ahead and see if that works as well in async HTTP. There's actually only one place we have to add it. Oh, come on, Adam. I don't know what's going on with my computer. So fast. Editor is not responding yet. Tell me something I don't know. Oh wow. Who is using all my CPUs? Streaming. How come streaming is using so much? Xorg. Oh gosh. Awesome. Reload. Keep waiting. What is my computer doing? Okay, let's just forget about that. Right, okay. Gem file. So we're gonna pull in the local version of async. And then what I want to do is I want to come in here to this connection. And this task is the background task which gets created. And this is a, or will, you know, there's not many gems that are written for async HTTP. Sorry, that are like async HTTP with HTTP2 multiplexing. The only one that I know of that's coming up is the async Redis gem with the RESP3 protocol requires a background reader. And so this is kind of uncommon because most protocols are very request response. Not that many protocols do multiplexing over one stream. I mean, a fair number do, but generally speaking, if you look at the top 10 protocols, most of them don't do it. And so what we need to do here is this background task should be transient. And so what this means is when your HTTP2 connection goes out of scope, this task will actually call the close method on the connection. And so we'll close the connection completely. And that's actually a good thing because HTTP2 cannot actually operate correctly without this background reader operating periodically. So if you leave your async block, the top level one that was running the reactor, the most logical thing to do is to close the connection. And this is kind of what enables it. So I actually have no idea if this is going to work. So let's run the specs and see how much of it collapses. So that's the pull being used for HTTP 1.1. And this is a particularly ridiculous spec, which makes some ridiculous number of connections, and there's no limit. It's internal only, so there's a server and a client spawned in the same process. And really all it's doing is looking at kind of a load testing. And so this pull says, I have 100 resources. There is no limit on the number of resources that I have been told to respect. And out of that, here are all the resources. And this number means how many current, the resources being used for this many current connections. And because this is HTTP 1.1, this number will only either be 0 or 1. This is the total number of concurrency that the resource can support. Because it's HTTP 1, it's 1. And this is the total number of times that resource was used. So if we look at HTTP2, it's a different story entirely. We have one connection we can make an infinite number of connections. There are currently 0 requests using that connection. Up to 128 requests can use that connection, and 1,000 requests did use that connection. So that's a really good result. It looks like potentially this code is aware, like it can work. And so what I want to do next is I want to try plugging it all into. Firstly, I want to go back to the pull implementation, and I don't want to just have that thing in a spec. I want to actually move it into the controller itself. And whether that's ultimately how it works, I'm not sure yet, but at least it will be okay for a proof of concept. The gardener. And then this is a little bit of a tricky one. This task will actually keep this pull alive forever until you exit the run loop. In actual fact, I feel like that should be a weak reference. But for now it's okay. For now it's okay. We might need to lazily stop that task. And recreate it as necessary. Because this task obviously has no purpose if there are no resources in the pool. Okay, so let's jump over to the GitHub Changelog Generator. And what we want to do is we want to find all instances of .close. Agent.close, and we're just going to remove them. We still need barrier.wait because we are waiting for those requests to finish. Otherwise, the data is not fully updated, and so that we still need that part. But it looks like that might be those 3, and that's it. Okay. Let's come to the gem file. Gem async. Async, and strictly speaking, we don't need the pull. So let's just try this to start with. I don't think there's going to be an improvement in performance, but I think it's a usability improvement. It's an ergonomics improvement. Users don't need to worry about when to clean up their resources, which is kind of the whole point of garbage collection, I guess. So actually, what branch am I on? Okay, I think that's okay. Bundle update. that looks okay. Now we'll know if this doesn't work because we removed the close statements, and if we weren't automatically closing the connection in the background, the whole thing will just hang. So we'll know that it doesn't work. So let's try running the tests. Run number of arguments, list issues. Maybe there is something wrong with the code that I changed. List issues, octo fetcher, 398 iterate pages. Is it the same one? Client issues, RB line 30, list wrong number of arguments. Definitely got the latest master, right? Given 3, expected 0, 2. Okay, what have I done with options? Client.send. Three, 9, 8. Method, user project, arguments, options. What version of Ruby am I using? That might be why. So that is a good lesson as to why some of this code needs to be reworked to handle options correctly. Okay, so that worked. I'm really happy with that because we made this code simpler and we moved the complexity somewhere else, and also that complexity is now more efficient as well because our ability to preserve the behavior or the scope, I should say, our ability to scope those persistent connections is improved, because if someone was to right now there are basically, like, I think 3 places where we have these sync blocks in this code base. And what would now be possible is to find where this is called. I'm just going to find somewhere random that this is used. Because this code runs sequentially. A lot of this code runs sequentially, and it should be possible to run more of it concurrently. And now we can put a big async block around all those individual requests. Not the individual requests, we can put like a big async block around those methods which are firing off all those requests. And we can then, instead of doing those methods individually, sequentially, we can now do them all concurrently. And so that's kind of the logic, that those methods, if they're closing the connection, that will cause problems for the other methods which could be running at the same time. And so that's what, for me, like, improving the concurrency is, it's important that the ergonomics of the resource usage makes sense. And I think this is a big improvement to that. So let's just have a go at generating this. If I can remember how it works. I love how there's two versions, one with underscores and one with dashes. It's like, you couldn't make up their mind. And one of them is not even executable. That's awesome. User project. Okay. User socketry project async. And then I actually do want to specify a token. Otherwise, it is ridiculously slow. And I don't want to reveal my token on a live stream. So just bear with me while I generate a token and export it as an environment variable. Okay. Awesome. That was pretty quick. Let's have a look at the changelog it generated. I think I should just overwrite this one. I've never actually had a changelog for async, so like maybe I should use this tool to do it. It's not particularly exciting. So that's really it. Let's quickly recap. And I think what I want to do is, I don't really like sitting on features for a long time, which I've written in the code. So, I'm feeling good about this. I might make a branch and play around with it a bit more, but I'm pretty happy with how it fits together. So let's just do a quick recap and then we'll finish there. I kind of want to test more complicated task trees to make sure I got the logic right. But I guess that's a bug. Bugs can be fixed. It's more like the semantic model, which once you make it available to users, that you start having issues with changes. Right, so this node is a node in a tree, and we capture transient tasks using this parameter. We have some accesses for that state. I might need to write some more specs. And we keep track of that state when we add children or consume nodes. And in particular, those transient tasks will move up. So grandchildren of a child that is being consumed, the grandchildren, which could be transient tasks, will move to the parent. So that means that the tasks essentially move all the way to the base. And the most important point is that the reactor won't be finished until all the work which is not transient is finished. And so once all the user's work is finished and we're only left with transient tasks, those tasks will be stopped. And so that kills the transient task. And so this essentially allows you to scope logic and behavior to the reactor, all the users' normal scheduled work being finished. And so that is a really critical point for when you don't know the scope of the lifetime for that resource. Another example of that is inside like a rack web server. If you're running inside Falcon, your persistent resources will be scoped to the entire server, the lifetime of the server process. But if you're running on a server like Puma, then your async block and your resources will be only scoped to that one async block. And so this kind of makes it trivial to write code that will run in Puma and Falcon, for example, without having to know what the lifetime should be. It's just handled for you. Then we have played around with Async Pull, which does all the pull handling for Redis and for Async HTTP, and shortly a database adapter, which I'm working on. And we have got this thing here, which can do pruning and close the pull when it's done. I'm still a little bit concerned about the lifetime of this task. There needs to be some way potentially to shut this task down. So, if you're making 50 pulls and then closing them, if they're garbage collected, this task needs to be terminated somehow. So probably inside this close method, it needs to release that task, to stop that task, and then when you call acquire for the first time on a pull, because a pull, if you close a pull, all it does is it closes all the resources. It doesn't actually make the pull unusable. I could do that, and then that would avoid that problem, but I like the fact that you can close a pull and keep reusing it later. What you're really saying is I'm going to clear out all the current resources. But maybe that semantic can change. Maybe once a pull is closed, it's finished. There's obviously this prune method here which can release resources which are currently unused, and maybe that can be improved. Then finally we came over here into the HTTP2 implementation, and we modified that so that the background task is transient, which means that when this connection goes out of scope, it will close rather than hanging. If you don't have this as transient, this task will still exist and the reactor will never be finished, therefore it will never stop. And so this minimizes the confusion around that. Lots of users have come to say to me, my run loop never seems to exit, and it's because they're not closing a resource. And so now with this change, they won't have that problem. And then finally, we put it into GitHub Changelog Generator. And with that change, there's no longer any calls to agent.close. And so it will close the Faraday connection, or it will close the adapter that Faraday is using as naturally as possible when the outermost reactor exits, which in this case is in one of those particular methods. But in theory, if someone decided to improve this code base further and put an async block around all of that code, those persistent connections to the GitHub API will stick around for the whole time and then be closed once the job is finished, which is it's the correct lifetime. So, for me, that's the right semantic model. Excellent. So I'm really happy with that, and I think I'll play around with it a bit more, and I think that's the right semantic model for managing the lifetime of these resources. And I think it will minimize the confusion and simplify the implementation of this kind of code, which is really, even though the complexity of adding transient tasks is non-trivial, like semantically speaking, having tasks which kind of exist until the reactor finishes is kind of a non-trivial thing. I think the value is really great. The ergonomics are really fantastic. Writing less code and getting better lifetime management is just, it's good. I can't see any downsides to that. Anyway, thanks for tuning in, and I hope you tune into the next one. Feel free to ask any questions, and I look forward to pushing this stuff out in the coming week. Excellent.